Hey, all right. In the previous video, we were discussing the first part of binary search tree. We just finished talking about how get successor works. It just gets the successor for the next node. So if I delete one, it's going to get the successor for that and move that up. And then, I would end up deleting another, and then I'd have to get the successor for that. Delete this, get the successor for that, and I'd just keep moving up left and right until the whole tree was full and back to normal like it's supposed to be. Now, that is get successor. Delete is the most complicated part here. So delete is basically going to be used to go through our tree, find the item we're looking for, and remove it. And you see it's actually quite lengthy here, just for the sole purpose of, delete is hard compared to all the others. Which is why I had to split this up into two videos. So we take a quick look at delete. What does delete do? Well, delete is going to remove one of these nodes. 8, 4, 5, whatever. I just don't like the way it looks. It's gone. It doesn't exist anymore. So I tell delete what I want to delete. I want to delete 5. Well, let's check. Uh, node parent equals root. Node current equals root. I get 2 pointers. Point them to the top. Right here. This is the root. Parent, current. We come back in. While data does not equal ID. So I'm going to look at current.data. Now, if I made that private, it would be current.getData. I'd have to use one of those methods. I made it public because I was lazy. Uh, if while I have not found the number, basically, parent equals current, and then I decide whether I'm going left, right, or I'm at the end. So effectively what this is going to do is just move me until I find the number. So all this code within this while is just, is the number in there? So we go through, and of course I actually have a method called find, which I could use that instead. It's actually fairly short. It has the exact same code we'll get to later, but I wrote it out here. So while I haven't found it, check to see if I need to go left or right. If the data I'm looking for is less than, or if the data I'm looking at is greater than the number I want, I need to go left. If I'm looking for a 5, but I'm looking at a 10, I go right. If I'm looking for a 10, but I need a 5, well, then I need to go left. So this will just move me to the left. Now you'll notice I have this Boolean called isLeftChild, and that means I'm at a left child. And I have to do something a little bit different if it's a left compared to if it's a right. Because remember, our delete moves right stuff up for the most part. Now, if it's not going left, then I must go right. Just like that. Now, if neither of these are true, or actually, I will go left or right. At the end of that, I'm going to check, is current null? Well, if current's null, I can't delete a node. It's not there anymore. I didn't find it, basically. So I keep going down this list until I find it. When I find it, that's when we're going to run the rest of this code, which will delete. If I don't find it, this returns false, which you notice this is public Boolean delete. I can't find it anywhere. Now at the end of this while loop, I should be pointed at the number that I want to remove. If that number is 4, then, or 2, I will cycle through this loop until I find that number. Haha! I found the number. This thing will end because current data is equal to ID, so the loop stops. Now if I'm here, that means I found the node. Now the first case, if the node to delete has no kids, no children. So if the current.left is null and the current.right is null, simple. I just basically make it empty. I wipe it out. I say, notice I say root is null. Let's click on that. Parent equals root, parent equals root. Uh, if current equals root, I should say. Basically, this means that if the current's the root, I'm at the very top of the tree, then that's gone. If there's a left child, then the left is null when I move that up. Else right is null. Depends on, where I'm going. So this first case is if the node I want to delete has no kids. None at all. If I'm at the root and there are no kids, then the root's just null. If I went through and I'm at a left child, then the parent dot left is null. It has no kids, I can do this. So effectively what this means is I'm here and it's null. I have no kids on this thing, so no kids this way, it goes away. Or if I'm here, no kids, I come back up to the parent, I make the left null. I come up to the parent, I make the right null. That's what's happening here. So basically I'm going to say, okay, parent's null, parent left null, depending on which direction I'm deleting. Or if the entire tree, there's only one thing here, and it doesn't have any kids, the root is null. That's the easiest case. Now case 2, if the node you delete has only one kid, one child, well, that's fairly easy too, comparatively, compared to what's coming up anyway. Else if, right here, current.right is null. All right. If current.right is null, then that means left is going to move up. So if the current's the root, I move the root pointing to the left now. So basically, what that means, if I'm here, I want to delete that, there's nothing on the right, then that means this left is just going to move up. Boom. That's it. That left is null. If there's nothing on the left and there's just one thing on the right, I move 10 up. Like that. And of course, I have to do a little bit of adjusting here, but for the most part, you'll see this whole tree just moving up, just boom. That'll be the root, and everything else is still in the order it's supposed to be in. So left, right, depending on which way is empty. Now, the fun part. That's if the right's null. That's if the left's null. All that is just which direction I want to go. Current, da da da. Now, the difficult portion. 2 kids. I'll scroll here. There we go. This is where we're going to use that get successor. There are 2 kids. We have to figure out which one is going to move up. Now, if current.left does not equal null and current.right does not equal null, that basically means that I'm like here and left and right have something there. Node successor equals get successor current. So basically, I'm going to use that get successor to figure out what's going to replace it. So this is going to run that get successor method that we went through. And it's going to return back the number that's going to replace. Now, if current is the root, then root is the successor. Else if there's a left child, then left is successor. Or I should say, the left gets the successor instead. Else, the right gets the successor. And then after this little if statement is done, successor.left equals current.left. I'm just making a little pointer to point to the other part of the tree because I'm removing multiple things. Return true. So get successor will run and find what needs to replace it, and then I will replace it. So, like I said, delete is much more complex, as you can see, because there's a lot of considerations to take into account. Insert, I go in here and just find an empty space. delete, I have to move items up and make sure they still conform to the rules of the tree. Less than is on the left, greater than is on the right. If that doesn't happen and somehow 10 gets on this side, then my tree is broken. It's not a binary search tree anymore. It may still be a tree, but not a binary search tree. So this is delete, while loop. My first set of ifs. Boop. Case 2. This case, boom. Doot. Case 3. And that is delete. So find, we could use in delete instead. I just added it just to add it. But this right here just does exactly what the first part of delete does. We go through and we try to see if it's there. And if it is, we say we found it. If we return false, then we did not find it. So if I keep going down this list and I hit null, it's not there. If I go down the list and finally it's not less than, it's not greater than, and it's not null, I found it. It's there. And that's simply find. Now, the traversals, you'll notice these are very, very simplistic. There's only a couple of lines in each one. Now, what a traversal does is display the entire tree, but it does it in a certain order. Now, this confuses a lot of folks, but let's take a quick look. So, if root's not null, I put that in there just in case the tree is empty. If it's empty, then we can't actually go to the left or right because there's nothing there. So as long as I am not empty, then I'm good here. So let's take a quick look and let's see. So notice we call in order left, we print, and then I call in order right. What I'm doing is I'm calling this recursively. So recursion means I'm going to call in order again. So let's see. I go left, print, right. So let's go to our tree and we'll see how this would normally print. All right, so if this was my tree, I call in order, I come here. I call in order left, and in order left's going to run before the print does. Okay, so basically this has in order left, print right. I got to run left before I can do the others. So I come here. This is going to call in order left, print right again. If there's a left, then I have to run that before I can do the others. I come here. In order left, print right. Well, there's a left. In order left, print right. Well, there isn't a left. It's null. So it stops with that. It's got to print the 1. I can't go right because there's no right, so I come back up. Now this, I finished the left. It still has print right, so it'll print 2. There isn't a right. We'll come up. This finishes the left. Print right, or what's left. I print the 4. And there is a right, so I'm going to go here. Left, there isn't one. Print is 5. Right, there isn't one. I come back. Now if you notice, I'm going to print 1, 2, 4, 5. We're going to come back up. And I just finished the left. Now I have to print 8. And then I have to go right. Left, print right. Well, left. Left, print right. I can't go left anymore. I print 9. I can't go right. I come up. All right. Left, print right. I'm going to print the 10. I'm going to go right. Left, print right. I can't print left. I can't go left. I'll print 20. So in order does exactly what in order says. 1, 2, 4, 5, 8, 9, 10, 20. It prints it in order. Another way you can think of this is basically it's going to go down to the lowest number, and then it's going to print, and then it's going to check the right and do the same thing. and then we come back up. As we come back up, this is when this thing prints, basically. As I'm leaving the node and going back to the previous one, I print. Boom, 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 boom. That's in order traversal. So let's take a look at post order or pre-order traversal. Same thing if it's roots null, we don't do anything. Now notice this prints first, then it goes left, right. So before I do anything, it's going to print. So let's take a look at my tree. And I've got, let's see here, print left, right. Well, I'm going to print 8, then I'm going to go left. I'm going to print 4, left. Print 2, left. Print 1, I can't go left. Can I go right? No. Come back up, can I go right? Nope. Come back up, can I go right? Yep. Print 5, I can't go left or right. I come back. So I printed 8, 4, 2, 1, 5 in that order. So pre-order prints as you go down, basically. And then it goes left and right. So print left, right. Well, since we finished left and we printed, we're going to go right. I'll print 10. I'll go here, 9, 20. So basically you can see it like this. This is going to print, and then you're going to have the nodes that are below it on the left side. 4 gets printed. 2 is below that, and so it's 5, but we'll print 1. 1's below that. And then it'll print 5. Come back up. So post order prints as you're coming back up. Pre-order prints as you're going down, post order as you're coming back up. In order, basically, a little bit different. Let's see here. There we go. And both of these are recursive. So actually, yes. I somewhat messed up the phrasing for that, but we go left and then we print and we go right for in order. So it'll print not necessarily as it's going back up, but as it's finished with the previous node, and then it goes to the right. Now, post order, we go left, then we go right, then we print. So let's see how that affects our tree. Left, right, print. I gotta go left. Left, right, print. I gotta go left. Left, right, print. I gotta go left. Left, right, print 1. I come back up. Right, print 2. I come back up. Right, 5. Left, right, print. 5 gets printed. So 1, 2, 5. And then I'll print 4. I'll come up. I have to go left, right, print. I went left. I go right. Left, right, print. Left, 9. 20, 10, 8. So the way this works is it prints the lower ones first and then prints the upper ones as you come back up. So that's pre-order, post-order, and in order. So to see that in actual code, actually running, let's take a look. Now I've got my regular insert, and I've inserted some numbers here. For argument's sake, let's say I go ahead and I insert these numbers instead of the ones I've got. 8, 4, 10, 2, 5, 1. Let's go ahead and just set those up. So we have the same numbers. 8, 4, 10. Let's think it was 2, 5, 8. And then we'll check the other numbers real quick. 2, 5, 2, 5, 1, 9, 20. 9, and then 20. There we go. So let's take a look. 8, 4, 10, 2, 5, 1, 9, 20. 8, 4, 10, 2, 5, 9, 20, and 1. Did I get that one? I did, yes. Okay, so let's take a look what this looks like. I have in order, pre-order, and post-order when these things, and I try to find a 4, which is in there for sure. So we take a little quick look at this. In order, and as I was inserting them, I have prints inserted 8 as the root. 4 got inserted to the left of 8. 10 inserted to the right of 8. 2 inserted to the left of 4. 5 inserted to the right of 4. So I got a little visual description here of how this tree is supposed to look. Now, I said 8, 4's to the left, 10's to the right. So let's take a quick look. Well, 8, 4 to the left, 10 to the right. That is true. 2 is to the left of 4. 5 is to the right of 4. 2 and 5. Okay. The 1's inserted to the left of 2. That's right. 9 to the left of 10, 20 to the right. So it looks like it worked pretty well. We print in order. 1, 2, 4, 5, 8, 9, 10, 20. That is indeed in order. And the numbers I believe I just jotted off for you for the pre-order: 8, 4, 2, 1, 5, 10, 9, 20. And then post-order: 1, 2, 5, 4. In this case, 9. There you go. 20, 10, 8. And that's how those traversals work. Now, I'm sure it's possible to go ahead and make one that could probably visually show the tree too. I wouldn't want to put, if you're bored, you want to give something a try, you could give that a try. You'd have to print that, and then you'd have to print the second rows, the left and the right of that. Then you'd have to print the left and right of that and that. You'd have to print the left, right, left, right, left, right. Basically, I guess you could use a loop that doubled every time. One node, print 2 nodes, print 4 nodes, print 8 nodes. And that may work, actually. It's entirely doable, but it would be a bit tedious, which is why I didn't throw it together. I think this is probably more than enough for most people in general. But there you go. That is binary search trees and its traversals.